Here we start to look at stoichiometry. Stoichiometry is the area of chemistry where we can do calculations that involve chemical reactions. And so, for example, if we start here with a relatively straightforward reaction, the reaction of hydrochloric acid and sodium hydroxide to form water and sodium chloride, we can see a number of things here. And we'll get to what these subscripts mean in a moment. But the first thing that this chemical equation tells us, it tells us that one molecule of HCl and one molecule of sodium hydroxide will react to form one molecule of water and one molecule of sodium chloride. Or as another example, we could look at the following reaction that says 2H2 plus oxygen reacts to form 2 water. So this chemical equation tells us that 2 molecules of hydrogen gas react with 1 molecule of oxygen gas to form 2 molecules of water. Now, just very quickly, we have these items here, and so let's define those before we move on to the next step. G tells us that the substance is a gas, L is a liquid, S is a solid, and AQ means it's in an aqueous solution. So that's all good. But again, to put this one back up here, how much good does it do us to think of it in the context we just presented? Again, 2 molecules of hydrogen reacting with 2 molecules of oxygen forms 2 molecules of water. Well, how big is a molecule of water? The answer is very, very, very small. In fact, if we think of a single drop of water, and this is one of those not so great terms that we use because, drop is a very subjective term. There's no definition of what that means. But a drop of water might contain somewhere on the order of 10 to the 20th molecules of water. And so if our chemical reaction is just telling us that it forms 2 molecules of water, not only is that less than a drop, but that's a quantity we can't even, we can't see, we can't even really, think about how small that quantity is. So it doesn't become all that helpful to sort of think of these things in terms of number of molecules. So we want to be able to do this in grams. But the question becomes, what's the relationship of molecules or atoms versus grams? And so we're going to take copper to start. If we look at the periodic table for copper, we find copper shows a mass of 63.546 AMUs. Now, what does that mean? So AMU, or atomic mass units. And 1 AMU is equal to 1.66 times 10 to the minus 24 grams. So again, this average copper atom, remember that average copper atom is coming from the ratios of the different isotopes that we discussed previously. If you calculate this out to grams, what that one copper atom would be in grams, we're still talking about a very, very tiny quantity. So we need some way to relate this to a laboratory scale. So we're going to define a new concept, or a new term, and this is the mole. And 1 mole of any substance is equal to 6.02 times 10 to the 23rd of that substance. And this is known as Avogadro's number. So 1 mole of anything is literally 6.02 times 10 to the 23rd of that item. So 1 mole of copper atoms is 6.02 times 10 to the 23rd copper atoms. 1 mole of sodium chloride molecules is 6.02 times 10 to the 23rd sodium chloride molecules. We could even think of it in any other context. 1 mole of elephants would be 6.02 times 10 to the 23rd elephants. So that's the main concept we're dealing with here, is that when we introduce this term mole, it means we have 6.02 times 10 to the 23rd of whatever that item is. Now, how does that help us? Well, let's see the following. So that copper, the average copper molecule, or copper atom, we just said 63.546 AMUs. So now we're going to convert from AMUs to grams. So 1 AMU is 1.66 times 10 to the minus 24 grams. And if we run that calculation, we now know the mass of a single copper atom in grams. But I now want to have an entire mole of copper atoms, so 6.02 times 10 to the 23rd. And when we calculate that out, we find that it's 63.546 grams. So now, that number that we find on the periodic table, we can use it in 2 different ways. And we're going to use one of these ways much more often than the other. As we said, we can think of it how we did originally, which is that 1 atom on average is that mass in AMUs. So the average copper atom, 63.546 atomic mass units. Again, that's such a tiny quantity that's hard to really envision. So much more practical and much more useful is that 1 mole of copper atoms, which is 6.02 times 10 to the 23rd copper atoms will be 63.546 grams. So now if we go back to one of our chemical equations that we started with, when we first started with this equation, we said that this was one molecule of sodium hydroxide reacts with one molecule of HCl to form one molecule of water and one molecule of sodium chloride. But we can also think of this as 1 mole of sodium hydroxide plus 1 mole of HCl reacts to form 1 mole of water and 1 mole sodium chloride. Similarly, the other reaction we looked at would say that 2 moles of hydrogen plus 1 mole of oxygen react to form 2 moles of water. And now we can use those quantities much more easily. They make a lot more sense in the context of the lab. So one of the things you should do is, as we're working through some of this, make sure you have a periodic table in front of you, because we're going to need those masses from the periodic table here with everything that we do in this chapter. So now, what would we say is the mass of 1 mole of copper? Now, in these first couple cases, I will bring up our periodic table so that we have it so you can see it more easily. But as I said, you'll want to have one with you to make life a little bit easier as we're doing these calculations. So we can read right off the periodic table. Copper, 12.011. So 1 mole of copper is 12.011 grams. Now, what about something more complicated than a single atom? So let's say methane, CH4. Well, in this case, we're going to go back to our periodic table. We see that copper is 12.011, or I'm sorry, carbon, 12.011 grams. And that's the unit we're going to use here is grams per mole. So 1 mole of carbon atoms, 12.011 grams. How about hydrogen? Hydrogen is 1.008. And again, that's 1.008 grams per mole of hydrogen. So what's the mass of 1 mole of CH4, or methane? Well, we need to take our mass of copper, and hydrogen, we actually have 4 of those. So we're going to multiply that by 4 for 4 hydrogens. Which gives us 4.032 grams per mole. So again, that's the average mass for 4 hydrogens. So now to find the mass for a mole of methane, we're going to add our mass of carbon and our mass of 4 hydrogens. 12.011, 4.032, and we get 16.043 grams per mole. So the mass for 1 mole of methane, 16.043 grams per mole. And we're going to call this term the molar mass. And again, we can do this for any molecule with any number of atoms in it. Again, we're going to go to the periodic table, find the relevant values, and add them together. So let's do another one. What would be the molar mass for potassium chloride? So again, we're going to need the mass of potassium and the mass of chlorine. If we go back to our periodic table, we find potassium 39.098. Chlorine we have over here 35.453. So again, all we need to do is now add those together. And we get our molar mass for potassium chloride. Another way to think about what we've now said is we've now said in this case 1 mole of KCl equals 74.551 grams of KCl. And you might be thinking, if you think back to our first chapter in this course, that looks just like a conversion factor. And you'd be right. And that's what we're going to be doing next, is we're going to use these molar masses as conversion factors so that we can convert from grams to moles. Because remember, when we look at those chemical equations deal with number of molecules, or even better, moles, but they don't deal with grams. So if we want to be able to do any calculations, we have to do it using moles.